I got stupid there for a second. All right, remember everyone, I do want you writing this down. I know you got a video, but there's no substitute for writing. My pen may also give out, and unfortunately my backup is one of the weird colored ones. All right, so I'm sorry if we just can't take a break. And remember, please try not to distract me too much with the email or talking, because it's just going to drive me nuts. But here's a little bit of a trick. You're going to regret what you said in your reviews. Every year I take everyone's photograph. So I will wait till all of you get down, stop for a minute, take your picture. If you have a warrant, lower your head. I usually put this on the internet, okay? All right, so I'll wait for those of you who are up there. We do need to get started. This is very difficult, 2 hours maybe, for you and me, because you're going to be writing all this down. And instead of 8 pages of notes, I have 16. All right, 8 pages on a typical Friday. I have 16 pages of notes. This is hard to do. All right, so actually, if those of you actually come down, let me go ahead and do the picture. I just want to go ahead and get things started like normal. Again, warrants, drop your head, you'll get caught. So, So anyway, now there's also a couple of you, if you haven't ever picked anything up, there's actually 2 of you who have literally never picked up anything. Maybe your grade isn't what you think it is, so you might, if you've always never done it, you might want to actually do it this time. So if you folks up there could find your things and let me get your picture. I just don't want to be distracted. You will not believe what bad shape I will be in your hand at the end of this lecture, all right? So, okay, all right, I got this side, I have to do this. I don't know how to do panoramas, so I have to splice it together. It takes me quite a bit of time to do this. I usually have it up on my website, so I'm telling you, be careful. Okay, we're almost done. I always have pictures of all my class. Every class I've ever had, I have all of your pictures as a record of the people who drove me crazy. All right. Okay. What's that? I saw a couple on Facebook of a giant chicken man. So, anyway, all right, God, folks, we're already behind. We are definitely already behind. Because you know, I'm going to go twice the pace I normally do. Hence the double shot. Okay, again, if you want to pick up your things, just quietly do that. And again, please don't be distracting right now. Please don't be talking for this one time. It's really going to drive me nuts. This is very hard to do. All right. Pens, you ready? Got your notepads? All right. Very beginning, there were gases. Oh God, I hope my handwriting isn't bad, but I do have to go fast. Am I going to ask a question like this? I don't really know. But this is what we did on the first day. We talked about isotherms. I'll spell it out. I don't have the kind of time. And, all right, what kind of question could come from this? Logic. I could do this, and I could do this. Now, isotherm means that these lines are drawn at a constant temperature. I can't really ask you to answer me because I simply don't have the time. This is high. High temperature, this would be low. Low temperature, easy. How do you figure that out? I ask you this, how do you figure it out? Higher temperature means higher pressure, bam, all right? Middle school students should be able to do that. Let's do V versus T. This is one that, that you see on television. This is the isobar. And temperature and volume are linear because they're across the equation in PV equals nRT. Again, now I'm going to ask something, maybe, all right? I'll drop some hints, but don't count it. I haven't written it yet. Sorry, that sucks, but I haven't written it yet. Okay, one's at high pressure and one's at low pressure. High pressure would be lower volume, so this is high P, low P. Okay, low P gave me higher volumes. Third one we covered is P versus T. Okay, and this is the one that you've never seen. This is the isochore. Don't think you have to memorize that word. That stupid. P versus T are across the equation, so they're linear. What gives me low pressure is high volume. Remember, isochore means volume, and this would be low volume because low volumes give me higher pressure. Low volumes give me higher pressures. Next thing we did Dalton's law. Really, Dalton's law. And this actually came up not so much during the first part of the class. It came up more when we were doing the delta G's of reaction, where we're pretty much going to end up. And that was that the total pressure can be decomposed into mole fractions of the various gases, times the total pressure. And this ends up being partial of A plus the partial pressure of B. I introduced that then, we never really used it, but it came up later. Okay, and that means that therefore the partial pressure of A is equal to the mole fraction of A times the total pressure. Okay, now we did PV equals nRT, which is for middle school students. Well, I guess high school students, son of a bitch. Oh, God, I hate to rub that back. But then you're in college, you're seniors, so we then did non-ideality. Okay, what was the source of non-ideality? It was dipoles lining up. Okay, things are polar. Even if they're not polar, like xenon, they can become polar by interacting with another xenon. And what that means is that you get a potential. Okay, now we normally label that V, but I don't want to confuse you, especially at this last moment. And we talk about how things line up, how close they are together, and what a real gas does. A real gas will do this, pretty much. Even if it's dipole-dipole or that dispersive interaction, that's how xenon-xenon interacts. And this just goes out and out and out. And so this is the attraction due to the polarity. And this is that thing you're going to cover, come on, this is the thing you're going to cover in 343. That's the exchange potential. Exchange is why things hit each other and they don't like to hit each other. And that raises the energy. Now, this is the same graph. A perfect gas doesn't do that. It's at zero potential and it stays there. All right, now that's actually how you derive PV equals nRT. That's how you do it in grad school. Right now, remember that what we did about PV equals nRT was not really a derivation. That was a phenomenological model. We just jumbled a bunch of things together and made them fit in the same room. All right, but the fact that this is necessary to the derivation has physical consequence. What could I do? I could probably ask you, I could throw this up there and say, tell me about perfect gases. Okay, well, they don't interact, right? Because you never drop, so this would be zero. Sorry, I should have done that. They never interact because this potential never drops into zero, but they never hit each other either. There's only one way to do that. They don't have a molecular volume, so they can pass right through each other. Again, I give you a graph, and you make logical interpretations of it. No derivations necessary. I am going to have derivations, though. You can count on this one. Van der Waals. Jesus Christ, I'm still on the first page. Van der Waals, remember that P is nRT. Okay, and then Van der Waals, as we're going to prove, introduced molecular volume by this term and attractive forces. That's the dipole-dipole thing. N squared over B squared. Now, some derivations that I haven't written the test, but I am very certain I'm going to do something with this. We also had the more convenient form where we divided by a number of moles, and this was very important for us to analyze what the equation was trying to tell us. Sorry, my handwriting will be pretty bad today. And, all right, so I can already see here that B is subtracting away from B. There's that by itself. I could ask you to do that crazy derivation. I'm going to repeat it, that we did to show that B was the molecular volume. But I can just already see that right here. Now, what would I ask you to do with this? Just some algebra. What's the algebra like? I could do this. I could multiply Vn minus B times every term, And then I could bring this guy over, and what does that do? That's going to factor P minus A over Vm squared, no, plus A over Vm squared. Okay, and what factors with that is Vm minus B, and that's going to be equal to RT. What do I do with that? I got Vm now is equal to RT over, I'm sorry, I'm painting myself into a corner, P plus A over Vm squared, plus B. Sorry, Vm I divided, and then I just brought over B. Okay, so this is exactly the kind of thing I would say. Okay, now if P is big, I'm not going to use the board very well today. If P is big, that's a big number. If P is big, volume is small. 1 over a small number is a big number. Big number plus big number equals no number. If P is big, I can still hear you, by the way, Vm is equal to B. All right, that's how we proved that B was actually due to the molecule's volume, because when you compress the hell out of the gas, there's still a volume. Why? Because it's solidified, and that volume is mostly the volume of the molecules themselves. Now, here's another derivation we can do. Oh, why did I do that? Another derivation I can ask that we did do. And that is, I can just say, if P gets small, sorry for the shorthand, then I can say, I'm going to write it again, RT over Vm minus B, minus A over Vm squared. If P is small, then Vm is big, and I can just ignore that. So that's RT over Vm minus A over Vm squared. Again, the logic is Vm has gotten huge. You know B is small, hopefully you remember, and this is the ideal pressure. And therefore, the pressure that you actually measure of the real gas minus the ideal pressure is going to be minus A over Vm squared. Okay, so what's important about that? A's were all empirically found to be positive. Those numbers that I gave you for A on the website, those were just people fitting numbers. What else are you going to do, right? So remember, A and B are fit. This says that the real pressure minus the ideal pressure is always a negative. That means a small number was subtracted by a big number. It means that the pressure under low pressure conditions is smaller than it should be. That's the way to interpret that. And that means that this is an attractive force. And I use the analogy of like a cluster galaxy, and all the stars are attracted to each other gravitationally. And that's why actually, when space expands, because we all know that the universe is getting bigger, galaxies actually don't get bigger. And that's actually the balance of space getting bigger and the gravitational interaction and the factoids. Anyway, also don't forget this. Now, I'm not going to cover this. I'm not going to do the derivation. Remember that we did compression factors and residual volumes. Compression factors were how far off of ideality, of the ideal pressure, than you should have gotten with PV equals nRT. And something like CH4 did this. And again, this is not something you should ever memorize. This is not 0. It's about 0.3. I just have these things memorized by now. Okay, perfect gas would be 1, because again, Z is how far off the real pressure you are from the perfect gas pressure. And something like hydrogen and helium were above. Now, my question I could ask in the test is, does this apply for all gases? Right? Is this true for all gases, that under low pressure conditions that the real pressure will be lower than the ideal pressure given this relationship? Well, now again, hydrogen and helium are the weirdos. Imagine I asked that a question again. That, does this apply for all gases? Now you remember hydrogen and helium always kind of do the opposite of the other gases when you include the real behavior. However, why this applies, I'm pretty sure it's actually still correct. And what would I say on the test? I would say that hydrogen and helium, the reason they're different is that their collisions matter most, because they don't have a strong interaction. So their collisions are always screwing them up. All right, but under low pressure conditions, they're not colliding. That effect would disappear, and A would then dominate. So, I believe that this is also true for all gases, even if it's hydrogen or helium. Remember we did residual volumes, and I'm not going to do that derivation right now. Last bit we started looking at isotherms, van der Waals isotherms. Let's do P versus V. And what's kind of interesting is that at higher temperatures, we get the normal behavior, but the nature of the equation, it doesn't look that complicated, but it does install lots and lots of curvature. At some temperature, it does this. I'll just remind you, this is high. That's high temperature, everything else is lower. And that, you probably forgot this, this is the critical point. Yeah, remember the critical point in our phase diagrams? That was it. So van der Waals actually predicted that in the phase diagram. Now, recall also that when you went lower than the critical temperature, you got this behavior. And what I'm seeing is volume decreasing and pressure decreasing. Yet PV equals nRT. That means that they have to work opposite, not with. So volume goes down, P goes down, that's nonsense. It is nonsense. So the equation is not perfect. It wasn't derived with quantum mechanics. Even then, it wouldn't be perfect. So people's solution were to draw that line. I told you not to remember this. It's called the Maxwell construct. Whatever, who cares? You just draw a line between it. And what you find is that you have this region where these lines exist, and then you actually put a substance at that pressure, at that volume, and we found a liquid. So a gas equation predicted liquid behavior. So that was really something that it could do that. Okay. Again, expect a van der Waals derivation, some kind of simple thought question about that. Definitely it is on the test. But let's talk about the monster. The monster in the room. The Maxwell-Boltzmann. Now, what am I leaning towards in terms of the derivation questions that everyone hates? I will do one, I'm probably going to do Maxwell-Boltzmann. Let me just straight up tell you that. I'm not going to do a Maxwell-Boltzmann and a van der Waals. I will not put those in the same section. That's asking too much from way back when. But this guy is too important. So, let's remember Maxwell-Boltzmann. Okay, Maxwell-Boltzmann. All right, we started out doing something that all of you can understand, which was the flip of a coin. So, what you can do is you say, if you flip a single coin, we're going to add 50-50 of one coin. And the odds that we see one side are 50%. Okay, and what's important about that is that if I can poke and prod a single coin, I can see its two sides. I can understand everything about it, because a coin, all I need to know about the coin is that there's two sides and there's no defects. So I am equally probable to land on one side or the other. And I understood that with a single observation. Problem, I'm gigantic. I've been eating more, but I'm so much bigger than this coin, I really don't have a good way to flip the individual coin. I have no choice but to observe a very large number of them. All right, so now actually it is true. God knows forbid, if any of you go into grad school in physical chemistry, we actually just recently developed ways to image single molecules. So this is actually largely becoming not true anymore, but it's been true for almost all of human history. Okay, now in all of human history, we can't even do a million, but let's say if we did 1 million coins, and the odds of that were 0.13%. 0.13%. So, now again, that's exactly half heads and exactly half tails. Of a million coin flips, or a million coins, same thing, that would happen 0.13% of the time. All right, now I'm going to be very dogmatic, and I'm going to just stick with probability. This says to me that either there's two sides, but there's a defect. And the defect means that it's not coming out perfectly. It's supposed to come out perfectly, but it does not. And so the coin is defective. The coin is not defective. I'm not thinking about it correctly. That's the whole problem. All right, now, the point here was to do 50-50. So again, I do a million coin tosses, and then I give myself a little bit of wiggle room. And that was a very small number, 0.3%. Then the probability that you do a million coin flips and you get 500,000 plus 0 to 0.3%, or 500,000 minus 0.0 to 3%, the odds that that happens is exactly 50%. Okay, so again, if you let, by the way, what did this? It was entropy. So if you let yourself have a tiny bit of wiggle room, then you will then understand that the coin has two sides and the coin has no defects. So, great. Now I understand that I have to not work with probability, but probability, really? Density. All right. So, then that means that basically for large numbers, and I wish I could write more. When I say that, I mean when I have large number of molecules. And again, for almost all of human history, I have to study large number of molecules simultaneously. Really no option. For a large number of molecules, you have to use probability density. Okay, and that's like the 50-50. The probability density is like the 50-50. And then what you have to do is multiply that by a spread. And then we get the thing that we understand, the actual probability. And then when I have the actual probability, then my eyes are open. Because if we were just smarter creatures, we're just not. We could look at probability density and understand everything. But we're just not that smart. We're too used to coins being flipped when we're children. So you multiply it by the spread, and then you get to the thing that us humans can actually understand. Okay, so how does that work? The problem is that that's like P of y, and then we have the spread. And if we use a very small spread, which you kind of need to do, then you've got this equation here. Now, again, I'm sorry I can't ask you questions, but I did bring this up, that this is unfortunately equal to 0, because a partial has no value. Remember, I asked you a lot about partials. Partials have no value, but they do have units. Don't forget that. It may come up. All right, so now how to interpret that statement, though? What's the probability of a gas molecule moving 300 meters per second? Exactly that number. It's 0. Right? Nothing is moving perfectly at an exact speed. So that's the physical interpretation of this statement. Okay, so now what we got to do is integrate the SOP. Sorry to write over my own notes. You have to integrate it, and then you get to the probability. All partials either need to be divided by other partials, or they must be integrated. Otherwise, they simply have no value whatsoever. Now, okay, last bit. Let's integrate over all values. Okay, and you know the answer then is 1.8. All values of y, because y is your dependent variable. And that means that if I say, what's the net velocity of a molecule from 0 to infinity, what's the probability that a molecule has a velocity somewhere between 0 and infinity, the answer is 100%. It has to be moving or not moving at all. And again, a 5-year-old could understand that. So that's the interpretation. Now, in terms of the final, look out for the trap. Remember, the biggest trap is when we do averages, and I'm going to get there in a second. When you do an average, and you forget to multiply this by y, I will cover that, I'm just foreshadowing. If you forget to multiply this by y, I designed the question to give you the number 1. That's the fact, that's the sign you did it wrong. That's the sign you just did this, which is very trivial. All right, so again, if I ask an average value, which I'm bloody likely going to do, and I'm bloody likely going to do not a average velocity squared, I'm bloody likely going to ask a how many salmon does Koki eat, because I want to see that you understand the big picture. Remember that if you do it wrong and you get to number 1, then you just simply were doing this, and that probably wasn't asked if I asked for an average value. Okay, now I did ask this on a test. Let's do Boltzmann. The Boltzmann equation. So Boltzmann figured out how nature partitions energy. And it's kind of like when we were doing coins, like when we had 4 coins, the odds of getting double heads was 1/4, because there's 4 possibilities, only one is double heads, ergo 1/4. Boltzmann then says, well, how does nature do it that way? Is it the energy of a state divided by all possible energies? And we can think of energies as being discrete because of quantum mechanics, which you're going to find out about next semester, but I foreshadowed. The answer is no. You do not do it that way. I don't know why. It's just how this universe was built. Instead, nature wanted to do it this way. Sorry, bad use of the board. E to that energy divided by all possible e's to that e to that minus energy. Okay. Why? Because if you don't do it this way, if you do it like again, just e to the I over the sum of e to the i's over all the quantum states. If you did it that way, nature would not be able to preserve mass nor energy. And that sounds pretty bad. But if you do it this way, it does. Ergo, it's probably correct. The derivation of this, I don't know if George is going to do it. It's pretty painful. That's why I didn't do it. One of the few times that I asked you just to trust me, that this is how it works without actually deriving it from some kind of first kind of principle. All right, so one problem with this is that I see that it has units, and I'm certain I will ask some kind of unit question. I really don't know what, but I want to make certain that you understand. I told you this many times. When you're confronted with something you don't really understand, knowing what the units are can be a very good way to figure it out. So, when we have e's, I know that I can use Taylor series to express e to the x, and it's 1 plus x squared over 2 plus x cubed over 6, and blah, blah, blah. I think that's right. And the problem with that is that that would have units of no units, that's 1, joules, joules squared of joules cubed, that can't happen. Right, when you sum equations, every compartment must have the same units in the physical sciences. It doesn't in anything else. So this is a problem. So we divide it by KT. Okay, sorry, not using this board well. Let's look at what K is. Let's see now, K. I can wane kind of philosophically on KT. It is really kind of important. The world has a certain temperature. The world has a certain temperature, and KT tells you the amount of energy associated with that finite temperature, that all things that have that temperature have. Everything has the same amount of energy if they are at the same temperature. Again, factoid of our universe, no proof to it. And KT is that number. K, remember, is the gas constant, 8.314, over Avogadro's number, 1.38, times 10 to the minus 23 joules per K. Not joules per K mole, that would be R. And now, don't memorize that, all right? You don't need to memorize that. I just want to tell you exactly how this comes about. And now another big picture issue. You know I like big pictures. When you see a K in an equation, oh God, good true and false question, not promising. Good true and false question. You see a K in an equation, that equation describes a single molecule. You see R in an equation, that describes a mole of molecules. And so that's why when we got to thermo, I'm sorry, we're kind of doing thermo now, but when we got to U and G and all that garbage, everything was done with R. Because another big picture thing, I didn't go over this, but thermo is a science of large numbers. Actually, I did say that once, but anyway, all this stuff that we do for U and G and H only works because we observe a large number of molecules. So that's why it's important to recognize when you're seeing a K and understand that that's for a single molecule, and understand again R is for a mole of molecules. When you do quantum mechanics, when you solve for wave functions, the wave functions you will solve will be for an individual object. You will only see K's. There will be no R's in the next class. All right, now here's the part that you all love. Okay, what energy do we use? We use kinetic energy. Why? Well, it's kind of easy. And easier than anything else we can try. I actually once tried to put in rotational energy into the Boltzmann distribution to get all this Boltzmann stuff for rotation. Oh, no, I simply did not have mathematical ability to solve that. So we chose translation, and what's good about that, we can do it. Number two, it leads us to the beginning of thermodynamics. If you recall, it's how we derive the partition function. We're getting there. Let me write this guy down. Now, we tend to call probability distributions the letter F, so I shouldn't have used a P up there before. That's a little bit stupid of me. And this is a function of Vx, Vy, and Vz. And we have a, okay, I'm going to have to drop to the next. Again, probability distributions must be multiplied by their partial. And the thing that you love, the reason I bring this up, by the way, is this 1/2 mv squared over kt. The reason I actually brought this up, because normally we actually do this in 344, is, to be honest, I wanted to scare you. I wanted you to see a giant equation and say, well, that's beyond me, and then show you that it wasn't. Okay, mv squared over 1/2 mv squared over kt. Okay, so in this way, I will start you out right, of seeing easier equations that came later and not be scared of them. So this is why I did this. And I also have to remember, now this could come up, now when I'm talking about the normalization part, right? The normalization part, just like in the double heads, we're talking about directions. And directions can be forward, and backward. And remember, that comes up if I ask a Maxwell-Boltzmann in a direction, you got to remember that forward and backward are both allowed. 2kt. And I'm missing my partial. Sorry, I'm kind of all over the place. And I can see that these are not all the same. And then I've got 3 of these terms because I live in 3 dimensions. Vy squared. You don't really, I wouldn't write this down if I were you, because you already wrote it down, and it's just a little too painful, and you think I'll have you write this all down on the test. It doesn't make sense, and it would hurt your hands. Okay, so I derived this, and again, because it does cool things, and number 2, scare the hell out of you, because it is a big scary monster, only to reduce it down. And I did show you that the bottom part, the normalizations, are sums. And again, those are sums over quantized levels. And you folks didn't seem to have a hard time accepting this, but some of my other classes did. When I told you that I do not move at any arbitrary speed, it just looks like I do. And let me foreshadow a little 344. That happens because I'm in a cage. Right, when you take 344, you're going to learn that the reason you have quantized steps in energy is because you are in a cage. I'm in a cage right now. Therefore, I cannot move forward nor backward except in discrete energies. So that's the sum. Now, the thing is, though, that it's not like I can only go 1 meter per second or 2 meters per second or 3 meters per second. That's pretty crude. I can go 1.001, 1.002, right? It's a fine grid. And because when you have a fine grid, sums turn into integrals. So we turn these integrals, sums, into integrals. They're just simple Gaussian integrals. I gave you the identity, and I will on the final for the Gaussian, for the Maxwell-Boltzmann question. And it is provable. It's hard to get the identity for Gaussian type equations, but it is doable. And what that meant was that big scary monster turned into this, m over 2 pi kt. And you may recall on the first test that I had asked you where this came from, and then I asked you where this came from. This is actually the part on top. Okay, because Vx, Vy, Vz, all that squared is net velocity squared over 2 kt. That's just 1/2 mv squared divided by kt. And then I've got dvx, dvy, dvz. Now I ran into the next problem. You can't solve this. This is unworkable. If you did, you would just have this, would just integrate to Vx, Vy, Vz. You can't do that. Why? Because it's actually in there as well. It's kind of like when we had problems where you had to integrate over volume times pressure. You can't do that because pressure depends on volume. So if you do that, you're doing it wrong. And we ran into that problem here because this has dependence on that. This is unworkable. So what we then did was we went to spherical coordinates. Again, why did I do this? Because 344, nothing but spherical coordinates. This, remember this, that's the Jacobian. And by the way, I have asked, remember that bit where we changed the dependence on velocity in the Maxwell-Boltzmann to like energy and momentum? I have asked that on finals before, just to remind you of that. Anyway, so because of the Jacobian of turning this into that, we picked up this term here. And remember that this is actually, this grows like an onion. So basically, you're multiplying this thing, which isn't that bad. This is a bunch of constants, and this is what it is. But you're multiplying this by the volume of an onion shell. That ends up being the area times its thickness, right? These equations can't make sense beyond just being a jumble of numbers. That is a real bastard to solve. And remember, this was done by Jacobians. Okay, now that I have a probability distribution, calculus tells me how to calculate averages. And you do that by this. Now, I am going to ask you to do this on the test. Or I'm going to ask something about it. There's no way I'm not. Times y times dy. Now, if you want the true average, you're going to have to do this over all values. Okay, now, you're on the test, and you looked at question 13, and it's Koki eating salmon. Now, the whole thing is setting it up and figuring out what the values are. Of course, I've told you what the values are. You just got to tease it out a bit. I'm going to be cutesy and clever about how I do it, and I'm not quite sure what I'm going to ask you because I haven't written it yet, but you know I'm going to do it. Okay, that allows us to calculate the average velocity of a molecule. Of a single molecule, right? Because I have a K. Okay. And, okay, and remember that's the mass of a single molecule. Again, if I do go there, if I do decide to go with this, I'm not quite doing that. Remember that's the mass in kilograms. Remember your standard SI units. Meters, that means volume is meters cubed. Pascals, not kilopascals. Kilograms, all right? So this is the kilogram of a single molecule. It's molecular weight in kilograms divided by 1,000 divided by Avogadro's number. And now here's the dangerous thing. There's so much you can do with this stuff. Again, I multiply this times what I want, integrate, and so what I want can be whatever I want. I was able to do velocity squared just simply by multiplying the whole thing by velocity squared, doing the integral, and then what I got was 3kT over m. Yeah, again, the mass of a single molecule. Now, here's a couple things. I can imagine a unit type of question on the final. Why is this square rooted and this not? Well, because this should be in meters squared per second squared, and that should be in meters per second. Therefore, I need to square this to get that. But they're not quite the same, right? And that's because 8 over pi, you don't really have to write this down, by the way, is 2.55. Okay, so I got 2.55, and here it's 3. Okay, therefore, velocity squared. Now, I'm going to have to take that to the half, because I can't compare two things if they don't have the same units. That just doesn't make sense. So I take the square root of this. Now they're on the same playing field, but this guy's bigger. And I actually went over this with my grad students. I mentioned to you the fact that this always happens is actually crucially important in the physical sciences. It'll never come up again unless you go to grad school. If you do, you will see this again. Because the differences between the two are the reasons that things have heat capacity. And if things didn't have heat capacity, I don't know what kind of universe it would be. It'd be pretty screwed up. So this is true for velocity, and it's true in general. And anyway, you know I like to throw things at you that don't always matter. Okay, so then, Then I introduced you, we did other things with this. Now remember, we did collision frequency, and I love that one. And then we did collisions with the wall. You know, collisions with the wall is not on the final. I don't care about that. Okay, if I do collisions with a wall, it's a formula, right? The flux, how many molecules hit a certain area over a certain time. What that would be is I would give you the formula, and I might do this with a couple of things. I might just give you the formula and say, hey, just work it. I'm just testing your calculator ability. But if you can't use a calculator at this point, what good are you, right? So I might do that. Now let's do collision frequency. Again, this might be how I do that. Now remember, we also saw relative velocity. I gave a handout on that one. That one was really hard. We had to do those Newton diagrams. Remember, that's how when two cars collide and they explode outward, people use computers to put them back together, and it says what the relative directions in space were. That's how you know who hit who. Now, this is way too hard for us to possibly derive in that final. That's painfully obvious. You should know that by now. All right, but this is what we got. It makes sense it's to the half because that has to have units of meters per second. And we had reduced mass. Get used to reduced mass. It's going to come up a hell of a lot in 344. That's what that is. And we were able to use that to show, for one, that relative velocity, I believe, was actually slightly greater than just net velocity. I don't quite know what to make of that, but that was kind of cool. That was one thing that we found out about that. But then we had this collision frequency. Okay, gas in a box. Gas is flying around, and they're hitting each other. And so how often do two things hit each other? And we did that by drawing out a cylinder and figuring out what the volume of that cylinder was, which actually depended on the relative velocity, and then calculating its volume, and then comparing that to the volume of two molecules. If they were the same, those molecules are hitting each other. There's no other way around that. Okay, and the equation we derived from that was this. And, pressure over kT, pi d squared. Now that is the diameter of the molecule, and we'll have argon, only argon, so they all have the same diameter. Oh, sorry, this is average. My bad, my notes. If you ever see my notes, I seem to be missing an average there. And, okay, an equation. All right, let's say I ask about this. I'll give you the equation. I just want to see you work it. I would like to do that because you have to get all the units here, here, here. You have to get all three of those right. So that would be a units type question. All right, but then there was something more important. I introduced you to a concept that was going to come up over and over again in the next part of the class. And that was, how is Z a function of temperature? That was the question. Okay, so I raise and lower temperature. How does Z change? Well, it's obvious. Okay, I got T to the half divided by T. T to the half divided by T is 1 over T squared. 1 over the square root of T. Right, so, right, I'm sorry, I'm doing this right. X to the 1/2 over X is 1 over X to the half. Okay, so I did that right. No, I didn't. See, that required, if P is constant. Okay, Z of T at constant V, if I'm going to hold V constant and increase temperature, pressure has to go up. Again, gas in a box, volume is constant, gas in a box. I'm heating it up, pressure goes up. Pressure is approximately linear proportional to T, PD equals nRT. Therefore, P rises linearly with T. In that case, I got T over T times square root of T. Square root of T. See, it changes. The result depended on what was held constant, right? And that was a big hint of things to come. And again, that might be a true and false question I would like to ask. Okay, now what we got from all of this, okay, different subject, what we got from all this is 1/2 m average velocity squared. That would be 3/2 kT, but now let's transition into 3/2 RT. Okay, The equipartition theorem. Right, so the reason, again, I do Maxwell-Boltzmann is because I can use it to prove the equipartition theorem. The equipartition theorem defines internal energy. Internal energy is where we start. And then everything else comes from there through Legendre transforms, which I'm also going to go over. So we have degrees of freedom. Okay, I'm going to have to use a shorthand. Freedom. Everything can translate in 3 dimensions, no matter what. Everything translates in 3 dimensions. Okay. Rotation. Sorry, let me do rotation. Now, rotation, the number of degrees of freedom depended on the shape of the molecule. Don't forget that. You should have learned this in freshman at one point, that the number of vibrations is 3n minus 6 if you're non-linear, and 3n minus 5 if you're linear. Now, with that, anyway, I'll get to that in a second. And then you have things like vibrations, but as we're going to learn, they don't count. Okay, and so, and now here's a big picture question. Okay, anything can translate at any velocity. Rotation and vibration, not so much because they're quantum mechanical. But before I get there, let me point out that the equipartition theorem says U is internal energy is 1/2, and we're going to go to R, T times degree of freedom. Okay. Again, it just seems to be how things were built. And if you just don't want to just accept that just as a blanket statement, well, I proved it with Maxwell-Boltzmann. I did do the limiting case of 3 degrees of freedom, 3 translations. There were no rotations in Maxwell-Boltzmann, so that didn't come out. All right, so that means that for translations, again, sorry I'm not using the board well, you always have 3. Therefore, U is 3/2 RT. Only if you can translate, but if you can also rotate, if you can rotate, that means that you're composed of more than one atom. It has to be. We talked about how you can't roll an atom. That doesn't make sense. Rotations depend whether you're nonlinear. Nonlinear is 3/2 RT. Remember, this is in addition, and that's nonlinear. Okay, so again, that's 3 degrees of rotational freedom. Why 3? Because we live in 3 dimensions. Same thing happening here, just a little harder to see. But it's actually plus 1 RT, and that is a linear. So it looks like I lost a degree of freedom. Why? Because that don't count. That's rolling an atom. So you lost one. In that dimension, it's gone. Okay, so there you go. So something like argon, its internal energy is 3/2 RT. Something like CO2, it's going to be 3/2 RT. CO2, that's going to be CO2. For those of you watching at home, that is 5/2 RT. And then for CH4, that was 3 RT. And these are what all the U's are. Okay. Now, let's see. What else do I want to say here? Okay, and then the reason that this happens this way is that this is a potential energy surface. This is energy. And this represents this axis represents rotations. In quantum mechanics, again, I'm getting you ready for 344. Quantum mechanics says that there's discrete energy levels. Okay. Discrete energy levels. And KT for rotations is like this. At any reasonable temperature, you can freeze things to the point where they stop rotating, but it's very hard. We can do it. But for the temperatures we care about, I don't live in a frozen metal box, and I never will, well, when I'm dead. But anyway, so what's important is why does rotations count? Is because they are heat sinks. It means that at any reasonable level of temperature that I'm ever going to experience practically, I can populate these quantum levels with molecules, meaning some molecules are rotating with this energy, some molecules are rotating more, some molecules are rotating more, some are rotating faster with more energy. Now, they won't be even Steven to the Boltzmann equation. That sounds like a good test. But they are heat sinks. I can put heat in and I can take heat out, and that's why they count towards you. Vibrations, no. Not unless we're building a rocket. If we're building a rocket, shit. Can we do 2 hours straight? Yeah, all right, no choice. I'm going too slow. So I might need just one tiny break. Vibrations, no. And that's because, and again, I look at energy, and then I look at vibrations, which is the same thing. It's like if I have CO gas, that's the CO bond. It has discrete quantized levels, but they're gigantic compared to little old KT. Up till, you have to get to the thousands and thousands of degrees before KT gets big enough to chomp more than one vibrational level of almost any molecule you could ever make. Any small molecule. So, or protein even. This doesn't work for solids, by the way, but I shouldn't even say that. But anyway, for little molecules like methane that we care about, this is so big compared to KT, it's not an energy sink. I can't ever take energy in, so I obviously never take energy out. So it might as well not exist as a degree of freedom. Right? The ability to populate these levels is really your degrees of freedom. And that's why vibration didn't count. And anyway, while vibration is shut out of the system, we still need to populate, we're still going to populate those translations and those vibrations. Sorry, those translations and those rotations. And you do that, U changes with heat and work. Okay, if you perform heat and work on something, and let's put energy into the thing, what happens is that those molecules start rotating faster and translating faster. They won't vibrate faster. Again, that's the point. And then we also talked about how they contribute equally to the change in U. So if I'm doing some work by heating, I'm doing some kind of change. If I'm compressing a gas, I'm doing a positive change, and that's going to increase, result in a change of U, which is also positive. And I'm going to remind you of all those positive and negatives. You know I was obsessed with that. So now the damnedest thing was heat. I'm going to put heat and work always like this, are inexact. And that happened to be path dependent. And we can say that, we can definitely see that in work, which is if something moves a certain distance, it did it because of a force. When you multiply the two, now you've got the work. Look, you have to know the path, right? I should have expressed it that way when I went over it, but you have to know the path. That's the path. It went up. Went that way. It went that way a mile. All right, so I have to know that to know what the work is, and they're path dependent. And again, I mentioned this to you before. I've never understood this, but they sum. The change in U is exact, and that is path independent. Path independent. And I'll bring that up a little bit more later. I'll talk a little bit more about path independence in a second, but let's look at heat and work. And again, there's all kinds of different work. There's electrical work. There's the work of twisting a spring, which is the same thing as stretching a rubber band, but I didn't go into those. I only went into pressure times volume. Why? Every power plant, every car works that way. Okay, a Chevy Volt doesn't work that way, but aside from a Chevy Volt, we're always doing, the most important kind of work is PV work. And so change in work was pressure times the change in volume. Now, I have to remember that this is actually a dot product. Because of that dot product, in IUPAC's made a decision to put a minus sign. It would have kind of been better had they not, because remember how TS, you always add TS and subtract, you always add PV and subtract TS when we do those other things. The reason they're different is because they simply slapped a negative sign on there. And that was kind of unfortunate. And the reason was they wanted compressions, which is energy storage, to be positive work, and expansions, the things that push my vehicle down the car, they wanted that to be negative work. Okay, now we then got into the two different types of work. And that was we started on the conditions. Remember, the conditions are isothermal, the reversible, irreversible, that's the first ones we started with. And we did that isothermally, and then we got into adiabatic, giving us 4 different types of conditions. So that's, you know I've said that for a long time. The different types of conditions. The easiest one, when I look at pressure, remember that is the outside pressure, that's not the inside pressure. I can make a sudden pressure, I can suddenly decrease the pressure on the outside somehow, and so now I'm at P2V1. Now I know that when I do that, then I'm going to expand to P2V2. Okay, so this is an expansion. Expansions are always a little bit easier to understand than compressions. And P times V, something I went over at the very first part of the class, P times V happens to have units of joules. And so when I have P times V, delta P, delta V is an area, right? Because P and V changed. So the change in work is going to be the change in pressure times the change in volume. So because of that, here's the change in pressure, change in volume. So it turns out to be the area. There's another way to do that. I've got a partial. Partials have to be integrated. If it has to be integrated, it's an area. So we know that stuff. Okay, and this was irreversible. Now, I just told you that at the time. You know now that that means that there was an irrevocable increase in the entropy, the total entropy. That was entropy of the outside and inside. It was greater than 0. I didn't say that because we didn't cover entropy yet, but that's why I called it irreversible. Later, when you did entropy questions, you found that the total entropy, in fact, did increase for irreversible transitions. Okay, and so that means to do the work is very simple. Change in P times, P2, in this case, work is just P2 times delta V. And delta V will be expressed, what am I going to have in the final? A gas is heated to this degree and expands, and so give me the work, give me the U, give me the G, give me the H. You know that's going to be in the next to last section. Guarantee you that's one of the questions. So irreversible, now there was a sudden change, nothing happened, so that's why it doesn't count. And because the P2 was less, there was an expansion, and the integral, because this guy was constant, the integral just turned into delta V. Okay, so irreversible isothermal was very easy. Now let me draw an isotherm this way. And this is when, so remember this is an isotherm. It has this much area. And the reason I would draw an isotherm is if the exterior pressure was made to match the interior pressure. Remember, I cannot emphasize this enough. This is the exterior pressure. This is the thing that counts. But I made the exterior pressure equal to the interior pressure. And the way I do that is hold the piston closed and slowly back off. And it won't be perfect, all right? Because when I do that, I'm going to kind of shake a little bit when I do it, but it'll be close. Okay, and then we learned that this was the reversible. Okay, reversible. And again, now you know that in the reversible case, the total entropy happened to be 0. I hadn't told you that at the time. And when we do the math, that does work out. It's always an awkward part about this, when I just start throwing out words that apparently have no meaning, but they do, but I can't talk about them yet. Okay, now, what do I want to say? Let me just remind you of the properties of the 4 conditions. I can't do that summary that I did that one time, obviously. I have too much to cover, and I am actually now on time. Well, okay, so reversible work is max negative work out. Okay, and I say out. When I say negative, that is the same thing as out of the system. And why was that important? Work in, well, that's energy storage. Yeah, but that doesn't do anything for you. Once you've stored your energy, which nature did for us during the Carbonaceous period of time, when all the oil and coal was created in this earth, nature stored energy for us. We're now springing it out at record pace. In fact, we almost got it all out. Then what? So work out is the work that is useful for us. The work in was done by the sun over the course of about 1 billion years. Okay, now here's the damnedest thing. Reversible heat is max heat in. Alright, that's positive. So when I say in or out, that's the same thing. Out is negative, in is positive. Max heat in. And I've never understood, I understand how to build a reversible engine. It would be an engine, again, that operates very slowly. It's me letting a compressed piston go very, very slowly. That's sensible. What kind of device is a reversible heater? I don't know. I think that's when you were freshman and you were, oh God, give me one moment. And you had a cup of water and you had a candle underneath it. You felt some warmth, right? Mm-hmm. Felt a little warmth, thank you for that. You felt a little warmth. Well, you were losing heat. I think that's irreversible. That's my take on the thing. Now, remember, I'm not going to do too much Carnot stuff, but in a cycle, change of U would be 0. Now, this is the part where U is a state variable where it is exact. So, and remember Carnot cycle. If you end up where you began, all your state variables, and that's pretty much everything except heat and work, pretty much everything else was a state variable, then the net change in those things is 0. It only matters where you are, not how you got there. And what that meant was, if however I set this up, and isothermal is the best way to do that, and that's one of those things you should just knee-jerk do, then this was true. And this is actually how I made this statement. Sorry, let me put the negative here. All right, maximum negative workout, that's not hard to figure out, and that's why I say this is the max heat in, because of this. Okay, then what did we do? Now again, remember that whole Carnot cycle was about building a perfect engine. There's not a lot I can ask about it. I may come up with a true and false, but the Carnot cycle was this giant diagram that got added up and was like a 10-step thing. But what was important was that the most efficient engine, the best working engine, is not a wound spring, but a reciprocating engine. And what was important about that is that when you're back at the beginning, all your state variables were reset. Okay, now, recall on the third test, I didn't have a derivation section. I had a good, bad, and ugly section, because I couldn't think of any derivations. I told you one of them. I gave that away, because there's no way I'm not going to add Maxwell-Boltzmann. But I am going to do this. We spent a long time talking about how functions change with their natural variables. You gotta know, you were probably sick of this. We spent most of the time on this. My handwriting came back. Oh, thank you, copy. Okay. Now, so what? Well, if I write the change in U as the change in heat plus the change in work, I happen to know that, again, because of this in a cycle deal, because I'm path independent, it just matters how I got there, I can always make the work reversible. Remember, this is supposed to be exterior pressure. If it is interior pressure, it is reversible. but I can choose it to be reversible. Why? Because it makes everything freaking easy. And now, I am not quite ready on entropy yet, but look, this is a review. You do know this, that is TDS. Okay, now I look at this. Changing a function, changing a function. I see my x, I see my y. But now I'm getting more. I now see that du ds is t, and that du dv is minus p. Did I get that right? Tell me I got that right. Du dv is minus p. Right, I got it right. Okay, sorry, I can't think right now. Okay, and so that's nice, and we did a lot with these types of equations, but one important one was that the order of differentiation of an exact differential is irrelevant. Remember, this is the Euler criteria. I don't memorize the word, but what that said was, if I differentiate a function with respect to x and then do it with respect to y, I could have done it in the reverse way, and they should have come out to the same thing. And so, one of the things that we started doing with these bad boys is solving Maxwell equations. Okay, and so, again, if you don't just have a natural feel for it by now, that's okay. Because just go back to this. I'll have this on the cheat sheet. And make it conform to that, knowing that f is u, and x is s, and y is v. Once you've got that, and df dy is minus p, not p, it's minus p. Can't forget that stuff. That'll screw you. That's how IUPAC screw to solve. The minus signs get in the way a lot. And they didn't really have to do it. Okay, so that means that the change y is whatever. The change, let's change u with respect to v, and we're going to hold entropy constant. But then we do the same thing with respect to entropy, and then if we did the opposite, if we did the derivative with respect to v of the derivative of u with respect to s at constant v, and also have to understand that the next step is done at constant v. Sorry, I kind of didn't give myself a rough enough room. This would be done at constant s. Now, again, even if you don't get this at all, you can look at the formulas and follow along. The udv, I gave it to you, it's right here, minus p. That means minus changing p, changing p with respect to s at constant v is therefore equal to du ds is t, so dt dv constant s. And again, let me double check, because I'm just kind of doing this off the top of my head, and I'm correct. All right. So, and then these ended up coming up in some of those other derivations. When I kept asking, how does p change with s, or s change with p, these were convenient ways to get out of sticky situations. Because you recall that s is the function s. Now, we have formulas for the change in s. I'm going over them, not quite yet on entropy. We have formulas for the change in s, but the s is a quantity itself. Not like work and heat. There's changes in work, there's changes in heat. There is no heat in work itself, only their change. That's not true of the state variable. You can change them, but they do have an absolute value beyond that of the change. But it's very difficult to know what S actually is, because it's K, L, and number of microstates. That does not mean I can solve this easily, but I might be able to solve that easily through things like P equals nRT. Okay, so we did a lot with U, and we figured out a lot about heat and work, but then we got to the Legendre transform. And the Legendre transforms took a function whose natural variables are x and y. And it turned it into a new function that, let's see, no longer depended on x, but its conjugate. And the conjugate is going to be df dx. Of course, that's at constant y. And we'll choose to leave y constant. And let's see, in that case, that would be G is F minus dF dx times x. Okay, so this is how you created a new function with the same units. Don't forget that, so these have the same units as well. These are all, we're going to make them all energies, obviously. And so I multiply the thing that I don't like times its conjugate, and I get a new function that doesn't depend on this, but depends on that. And why was that important? Because, if you recall, the changes in these things were important when you held one of the natural variables constant. Like when I held volume constant, U turns into heat, and I power the world with heat, so that's important. But I have to hold something constant, and then it turns into something actually really quite useful. If I hold them both constant, U represents the negative of total energy. Better yet, the negative of total entropy. Better yet, the change in total entropy, system and surroundings, becomes negative U. Meaning, if U goes down, total entropy increases. Total entropy increasing is what defines if things happen. So, now, problem. I can control V by putting a reaction in a metal box. It's not advised, but it can be done. But I cannot control S. Unless I do something adiabatic. Now, in that condition, you actually can't. Adiabatic reversible, but it's actually hard to build mousetraps that are adiabatic and reversible. In fact, it's just freaking impossible. So I can control V, but I can never really control S. Kind of. People are pretty clever, and people have built this thing. You can Google search it. It's called a Stirling engine. It is almost a reversible engine, but it's very hard to build, and it's very impractical to build a car out of it. So I need to get rid of this S dependence because I need to have something that I can control and get a handle of a certain energy function that will go downhill, and that way I know whether it happens. Because if I hold the natural variables constant, again, that thing turns into minus total entropy. And in this case, all right, I need to Legendre transform from U. I need to get rid of the S dependence, and that happened to be U minus S. The conjugate of S is du ds, and that's T. All right, like you're used to seeing it. Okay, now that's a Legendre transform, and that means that A, I'll do a full example. Now, I hope you can do this, figuring out how you turn these changes into all the PDVs and TDSs. I always remember that A is the one that's always fully negative. And, okay, so now I get the internal energy through equipartition theorem. That's not too hard to do. Temperature is whatever the thermostat has set. You see, this is why I don't have an entropy regulator, but I do have a temperature regulator. In fact, I have very good temperature regulators. Now, I have to know entropy, and that's the hard part, but we do have tables with all the chemicals we could ever handle and their entropy. They do exist. That means I can calculate A, and then I can see how it changes. I can see how U will change through the equipartition theorem. T, I'm cooling it, so I control that. And S, well, again, I have ways of calculating the change in S. So I can know whether A goes up and down when I'm holding V and T constant, which is very easy to do. Now, I just said, I talked about changing T. When I'm talking about, and then I'm talking about holding it constant, I mean that I want to know, I know that my chemical process does not function at my temperature. If it was lower and then held constant, would it work? That's the kinds of things we can answer, which is pretty important. All right, now then remember that we had, so this means that it's a function of V and T. You always look there. Even if you don't really follow this, you just look there. Then we had all the others. Actually, we started with, of course, enthalpy. And this ended up being not a minus, but a plus, because the conjugate of V is minus P. That's why I keep harking on minuses all the time. And therefore, the change in H was, it still kept its TDS. It's still dependent on entropy, so it was never exactly very useful. But now it depends on pressure. And if I held pressure constant, I believe it was heat. G, and so I've done A, and G is U plus PV, a double Legendre transform. That's why G is always a little bit harder, and therefore the change in G is minus SDT plus VDP. Okay. And then we talk about the utility of these things. I already mentioned, of course, about total entropy. I'm going to go back to that. I was just foreshadowing, and you do remember, hopefully, how all this stuff works. Okay. Okay, and then this is the change in heat plus the change in work. And do not forget how to do these. Plus PDV plus VDP. What product rule in calculus. Right, that's exactly what that is. Okay, now, heat is heat. I don't know that I have the greatest expressions for that, but work, because I was friendly and made PD work the only kind of work we were going to consider. I just write the rest of it out. Okay, cancel, cancel. And now I see enthalpy is a change in heat plus VDP. And if I held P constant, therefore enthalpy was equal to heat. Okay, just an example. Now I said, if I ask this, hey, what happens when I hold P constant? You say, well, that's kind of neat because it's enthalpy becomes heat. Now, if I say to prove it, you kind of need to do this, and that's probably what I'm going to do. Sounds like the first one's a true-false question. The second one sounds like it's a derivation question. And then we got into heat capacity. Then, sorry, let me just put this here. At this point, because this was our intro to entropy, and enthalpy, changes. God, I'm sorry. Changes in enthalpy, because heat is always a change. Because I don't think heat things up or cool them down. I don't stare at an object and use the force and increase its heat without a temperature change. That's stupid. That doesn't make sense. Okay, and actually I should have started with U. Constant V was heat capacity at constant volume. And now remember you had this on homework. Since for AR, U is 3/2 RT, again by the equal partition theorem. And so I've got, again, all my state variables have functional form. S is a Bisnacker, but U has this very simple expression which anybody can understand. Now I put that in here. I've got CV is the change in 3/2 RT with respect to T, and that's 3/2 R. Excuse me. Now remember that this would not work if R somehow depended on T. Now 3/2 is 3/2. If R depends on T, you can't do this. You'd actually have to use a product rule. But it doesn't. It's a constant. So this is perfect. It is absolute mathematical and scientific perfection. So, and then I look at argon and I measure its heat capacity, which I can do very well, and it is almost exactly 3/2 R. And again, this is a very simple question I could ask you on the test. Now, remember that some of the heavier ones, like xenon, you saw deviations. Now, I said it's perfect, but it wasn't perfect. Well, why not? Not on the final, all right? But just, again, 344 stuff, it's because knowing what a degree of freedom is actually incredibly difficult. I remember telling you that argon, remember how argons can do that whole pair-up thing through dispersive interactions? They actually vibrate. We actually had this really big-name guy from the University of North Carolina come to our department to give a seminar where he actually measured the vibrational spectrum of argon dimers. That would actually count as a degree of freedom, but it goes and comes, right? So our understanding of degrees of freedom is too absolute. We're just not smart enough. We don't think quantum mechanically. It's very difficult. That's why I'm always prepping you for this. So I guarantee you that all of this works. It's just that I don't always have this part right. And that's why we saw derivations in heat capacity for simple molecules, especially for methane. Methane will, of course, be 3R. It's actually a good bit higher. Again, because I don't really understand all these degrees of freedom. It's simply too difficult. Another thing we went over, and this was a very long derivation, this is what I was trying to start to scare you and get through to you, that we're going to be doing lots of derivations, lots of this stuff, right? Lots of derivations. Was CP being greater than CP? I'm not going to put that on the final, all right? That one's hard for even me. That was the one where we had to do one derivation, we got stuck, and then we had to go do another derivation, and we added them together. Look at the video if you don't remember. If you can do that one, you can definitely handle anything I throw at you. All right, but CP is greater than CD, and I would probably ask something like why? Answer. To hold pressure constant if you're heating something, and why am I talking about heat capacity unless I'm heating something? To hold pressure constant, I have to let the balloon expand. And that means that there's work, and that means I'm turning heat to work, which is a loss of heat. Whereas in the metal box will get hot really, really freaking quick. So remember, a small number means hot quick, a big number is a damp. It's a damping force that means not hot so quick. And that's because work was done that took the heat. Not all the heat, right? Yep, that's the second law. Okay, then we got into adiabatic. So we've talked about, this was all kind of a lead up to entropy. And even though thermally insulating, basically we've covered isothermal, reversible, and irreversible. And don't forget, again, I'm not writing out all those equations, but it is going to, like I did that one day, it is coming up. So you can't imagine I'm not going to do that. So then we did the adiabatic. And that's when, remember when I asked this question? If I ask a question, you write that down instantly. And if we look at adiabats, understand their nature, I know that isotherms have this nice little curvature. But an adiabat, starting from the same place, slopes harder. And these are actually, instead of isotherms, these are called adiabats. And this is something I forgot to mention at the time we were doing this class. The time we were covering this, sorry. Okay, they slope harder. All right, so I thrown this graph at you at the final. Why? Why is it slope harder? Because I've got it thermally insulated, and this is an expansion. Expansions are always a little bit easier to understand than compressions. I don't know why, but that's at least how I think. All right, if I'm expanding, I'm thermally insulated. Because the change in heat is so narrowly defined, it doesn't mean that heat doesn't still exist. It's just inside, it's trapped. So to do this expansion, it's using up its own heat. And in an isotherm, it doesn't have to. The isotherm is going to change some work. It's going to do some work, and that's going to be negative work in the expansion. But it's got to be balanced by a change in heat, or the change in U would not be zero. And it has to be because of the equipartition theorem. Okay, so the isotherm has to have heat come in. Again, it has heat come in to cancel the change in work. Heat goes in to cancel the change in work to keep U constant at isothermal conditions because of this right here. That stays the same, that stays the same. All right, so thermal transitions had heat come in, that meant they had higher pressure. Again, exactly the type of question I would ask, just to see that you can generally understand this stuff. Now, when we were doing isothermal, work was minus nRT LNVF over VI. I'm not going to write it down. I should have written it down up here. Remember, minus nRT LNVF over VI, that's work under isothermal conditions. Under adiabatic conditions, work is the change in U, and the change in U, because I simply have nothing else to work with, is going to be, it can be at constant pressure or volume. It could be either. Okay, but you know, I'm going to just stick with constant volume. The one time you saw it being a change of constant pressure was when I talked about heating an anvil. Well, I'm not going to heat an anvil inside a giant metal box. Why the hell would I do that? So that anvil is under constant pressure conditions. All right, so if I wanted to do the adiabatic work under constant pressure conditions, that's when I'm heating an anvil, then this has to be CP. But I'm not going to do that to you. I just wanted to let you know that it does exist. I'm always going to stick with CP. And if you screwed it up, I just won't even count it wrong, in all honesty. Okay, now that meant that when you do all adiabatic, if I ask an adiabatic question, That is the thing you must get to next. You got a point there, but now you've got to get to that. If you can't do that, you've lost a point, and if you do everything right from there, you've only lost a point. But that isn't going to be easy to do. So just don't forget that. Just practice. Look at those problems and redo them. Now, just because this is now work doesn't mean that this did not go away. Okay. And this is what you solve if you are irreversible. I know that because of that. It's exterior pressure. So there's been a sudden change in exterior pressure of a piston that's wrapped in glass wool, right? That's me reading this equation in words that make sense to a 5-year-old. Now remember, I once asked you about compressing a piston. Just so you know, this is the type of question I like to ask to test your understanding, your general understanding. I once asked you about compressing a metal piston. It got hot, but you let it cool down, but then you wrapped it in glass wool, and I asked you what happened when you let go. And about half of you said nothing happens. Well, that's ridiculous, because you could pressurize it to the pressure inside the sun. You can pressurize it to an unbelievable extent. So what if it got hot and cooled down? It's still going to expand like a rocket. So just remember those kinds of things. Now, when you're irreversible, you solve this as it stands. This is going to be integrated to delta t. This is integrated to delta v. You related delta v to delta t. It actually was kind of hard. Look at the example problem I put on the handouts. Look at the questions I asked. Despite being the simpler of the two equations, it actually was slightly harder. It's just a lot of calculus. Now, if you were reversible, then in that case, cv dt happened to be nRT over v dv. Okay, that one certainly looks easier than this one. This one ended up being actually not so bad because, again, getting to the change in temperature, getting to this, which gives us so much, what I found is that I'll figure it out by this equation and variations thereof, which we just use PV equals nRT to do that. I'm not inclined to ask you to derive that on the test. I think that's asking a little too much for a final, but it's not that bad really. And I've given you this, I've given you that, I gave you CV, I gave you N, you already know R, I gave you TI. I have to. I can't set you up with a question with no answer. I've given you all that. You had to find TF. That's why the irreversible is a little bit harder, because I didn't in that case. But okay, so that gave you the change in...
negative sign. It's negative nRT over here, right?
Yeah, sorry. Yeah, looks like my notes are missing something. Anyway, my bad. Thanks for catching me there. Yeah, of course it is. And that's why, actually that's ultimately why you had F over I and I over F, actually. Thanks for catching me there. Okay, so again, I can't emphasize enough that obviously I'm going to ask a gas expands under adiabatic conditions from 4 liters to 5 liters. It's argon, so its heat capacity is this. I will have hidden like N by having given you PV and TI, and then you can find N. This is kind of little clever things I like to throw in. And then I'm going to say, give me change in H, U, S, S total, S internal, S external. Anyway, okay, that led us to entropy. I might have to hold you just a little bit longer. And that gave us this, remember, an actually incorrect equation, but I just don't know why people are like this. Chemists are like this. Just want to remind you of the Clausius inequality. It gave us this definition for the change in S. The change in reversible heat over temperature. And remember that we also did that horrible, now again as test-taking strategy, remember we did that horrible thing where I showed that heat is inexact. It was pretty painful, but heat over temperature was exact with the Euler criteria. That was very painful. I'm not going to add something like that. But anyway, this is our narrow definition. And remember the Clausius inequality. If the path happens to be reversible, of course, then these two ought to be the same. But if a path is irreversible, then this guy has to be greater than that guy. So, I hope I got the sign right. Someone maybe should check that. Now, then that brought up the second law. Remember, the first law is you can't turn, energy cannot be created nor destroyed. That's actually why the change in heat is equal to the change in work minus the change in work. That's actually, energy can't be created or destroyed. The second law had two statements: can't turn all heat to work. Okay, so this one's unusual. So if I ask this, give me the three laws of thermodynamics, you say energy can't be created or destroyed, pick one of the two. There's this one, this is the Clausius statement. In a spontaneous process, the change in S total has to be greater than zero. And technically, I don't think that would have an equal sign as well, because that's an equilibrium process, and I don't know that equilibrium is the same thing as spontaneous, because equilibrium, nothing's really happening. Okay, so that was the second law, two ways to say it. If I ask that question, pick one, and it's right, because in a weird way, these are actually the same thing. We talked about the Carnot cycle here. Again, if I was to ask a Carnot question, I'm going to ask an efficiency question. I'm not going to ask you to draw it or solve it. That's painful, but that's what we got out of the Carnot cycle. And then this is, does it happen, does it not? And so I kind of consider this one more important, but they are actually identical. It's just really hard to see. Okay, then we had to calculate the change in S, and this is the system. And then we had to come up with a bunch of different rules for the surroundings, and then we added them to get, together to get the, the total. And those just followed certain rules. The total was always zero if the process was reversible. The total was always greater than zero if we didn't know it, if it was irreversible. And all of them were zero if we were doing adiabatic reversible. And so what we'll do is integrate them. That makes us delta S. Sorry for going backward. Delta S is the integral of this. That's the integral of that. And I know heat can be CV dt and over T. And that's easy. Again, don't forget that I'm going to give you heat capacities in terms of their molar volume, but heat capacities are extensive. So don't forget that. It's a common mistake that I give you half a mole, but you use the molar heat capacity constant volume. You just lost a single point. That's all, not bad. And this is at constant volume. Because you know that, delta S heat plus volume, if heat and volume are changing, I've got what I just did, CV, ln, TF. Notice I've written it differently because I didn't make that the molar heat capacity. And then we had NR. And of course you know that this is on the cheat sheet. And actually this guy comes about because I can always relate the change in heat to minus the change in work, and you may notice that's minus the change in work, reversible change in work, divided by temperature. And anyway, so remember now, the other thing was, again, this is the system entropy, and it works no matter what. And so it's like we're done. We're not done. So remember, isothermal reversible. For isothermal, that's gone. Calculate that. Half the battle. But I've asked you the change in the outside entropy. Now, I don't have an equation for that, but I do. I just have to remember that if I'm isothermal reversible, obviously this is zero. Go ahead and calculate it. It's zero. I've calculated that. I've gotten a point. That's the system. The surroundings have to be minus that because the total must be zero because I was reversible. Okay, if I was irreversible, I've got this, and let's say it's negative, then the surroundings was greater than minus that, so that the total was greater than zero. I only know that the total is greater than zero. Sorry, I can't write this down. My arm's about to fall off. Okay, adiabatic reversible, everything was 0, right? And I showed you that you can still use this equation and you still get 0. You know the total is 0 because I said it was reversible. Therefore, the surrounding was also 0. It has to be 0. The adiabatic change in the entropy change of the outside in an adiabatic process has to be 0 because it's thermally insulating and there's no change in heat. The outside was completely oblivious to the inside. Okay, adiabatic irreversible, if I go there, I'm not tempted to, but I reserve the right to do these things, then you actually have to calculate both, and you will find that while the outside is still 0 and the surroundings is 0, that this was positive, and if it's negative, you did it wrong. And remember, I set you up on a question where hardly any of you answered it the way I wanted you to. I gave you a set of conditions and said I was wrong. That's because for an adiabatic irreversible transition, it was because the total change in system entropy, which is the only change in entropy, was negative. So that was just a little trick I did. Okay, last bit, that S. Okay, you guys don't mind if I hold you a little bit longer, I hope. Well, there's going to be a choice. Okay, now this, of course, okay, here's a good question. Here's an equation. Here's the statistical mechanical definition of entropy. And that's K, the Boltzmann constant. So this is the entropy of a molecule. So it'd have to have the number of molecules. K, ln, number of microstates. Now, I talked a little bit about how you really do that for gas. The number of microstates is actually like the volume. Keying on a chessboard, that was easy to know. But overall, unfortunately, a fairly complicated thing. And that's why when we do changes in S, I can't be doing this. Well, I can. It's just that this thing depends on temperature, probably in an impossibly complicated way. And while maybe I can solve it, then I could do this derivation. Maybe I could do that derivation, but I'm telling you that is going to be an impossibly difficult thing. That's why Maxwell relationships are very, very, very useful. Okay, remember, increasing total is the same as decreasing G at constant P and T. Make a little diagram here. So remember that whole Clausius inequality bit. That was important because it defined when things were spontaneous. Something is spontaneous, it happens. That's kind of important to know. And because G at constant P and T, I did the Clausius inequality, and I found that it was equal to the change in G was minus the change in total entropy. A was associated, if it decreases, total entropy is going positive, which is good, but I had to hold volume and temperature constant, which is possible, and it's actually how a power plant works. We're never going to hold entropy constant, and that's why H and U are never really very useful. But I can ask you that. I mean, technically, adiabatic reversible, if I want to know whether that happens or not, then there we go. I'm not looking at G anymore. Okay, getting closer towards the end, because you know, I am biasing the test heavily in this direction. Very heavily in this direction. I'm going to definitely ask a derivation along these lines. So I'm just going to throw at you some kind of tell me how U changes with V at constant T. All right. This is on the cheat sheet or it's in the question. I said, hey, how does U change with V at constant T? So you write down U. You just add these guys. Okay. Now you got to be savvy here. And know that that's 1, not 0. This guy, wiped out. Remember that? Isothermal, changing U is 0. Volume can still change, so that's finite, but that is 0. 0 over whatever is 0. Okay, so that leaves me with T ds dV, constant T, is equal to P. Hopefully I'm doing that right. Therefore, ds over sorry, let me do this a couple of times. The change in S is P over T. Again, this is exactly the kind of derivation I might ask you to do. Okay, now if you integrated this and say, okay, delta S is P over T times delta V, you got half credit because you have to do this. NR over V dV. And then, when integrated, you get NR ln VF over VI. Again, just an example, but exactly the kind of derivation question I will probably ask. Again, a Maxwell Boltzmann and one of these suckers, because I like them. Okay, third law, stated through the Nernst theorem, is that S is 0 if T is 0 for a perfect crystal. Now that's because knowing S is incredibly important that we measured it. We measured the absolute entropy of everything we can get our hands on, and I know that it always increases, and it looks something like this. Increased at first, then we get phase changes, which represent sudden changes in entropy at a constant temperature, because water boils at 100 degrees, always. Then it increased again, then we had another phase change. It's always increasing. So we froze things, measured the heat capacity, integrated it to get everything's absolute entropy for everything we could get our hands on, because entropy was so much more important than the rest of them. And that was the second test. Again, the final will be highly biased towards everything I've said. Then we got to the third test, which is chemical potential. And chemical changes in chemical potential were terribly important. And that was if P and T were all constant, and if A is equal to A, just as long as you hold B and T constant. And we talked about how things at equilibrium have the same chemical potential, and if the chemical potential of something is greater than the chemical potential of the other, then A turns to B. The higher one loses. Energy always goes downhill. Remember that we then entered a constant P and T world. In the constant P and T world, G was everything. So we did everything with G. Now that also, so we've been covering what's this substance G, and we'll talk about a gas. I got a mole of gas in a container. That container is at STP, right? Remember, 1 bar, 25 degrees C. So it's at STP. I want to know it's G, energy, and I look at the table. Because I'm under the right conditions. As soon as I go off the right conditions, that number does not work anymore. So I have to make alterations, and I have to know what they are. So the chemical potential of something will be that number in the book, plus some kind of change. And unfortunately, I have to work with activities. A is activity. And why is there a change? Because I mixed two gases together. And so I've gone from its pure partial pressure, and its partial pressure, now that I've mixed it with something, its partial pressure has changed. Remember Dalton's law, I said it 2 hours ago. Now, remember that the numbers in the book for our gases and everything were done at 1 bar, even the gas. So, there you go. And that meant that when we talked about a chemical reaction, for A goes to B, A goes to B, then the reaction G was per mole, because chemical potentials are per mole. The chemical potential of B minus the chemical potential of A. It's the delta reaction of the thing we taught you in high school. Just look at the numbers in the back, in the table in the back of the book. But really, you had to make a change. And this was actually an entropy deal. And don't forget that we have to raise them to the power of the stoichiometric coefficient, like I failed to do in that one homework set that I still regret. Anyway, there you go. Okay, and remember that A is on bottom because its molecularity is technically negative because A went to B. This guy is negative, so that's why it sits on bottom. Now at equilibrium, this was true. And then what we ended up with is, I just brought delta reaction G, because equilibrium is important because that's where a reaction stops. And that tells you how much products you get. I hope you remember this little terminology, this pi. It means don't add everything together, it means multiply everything together. And again, your reactants are on bottom because that happens to be negative. And this guy was, of course, K. K, the equilibrium constant. And I hope that I have an example, but I am just about out of time. I want to do electrochem. Hopefully this is fresh in your mind. We really were here just not too long ago. And so, where am I? Sorry. Let me just, where have I got? Sorry, folks, just work with me 1 second. Yeah, okay, so I hope you can work these problems. We did them not too long ago. We then went to electrochem. I will try to end on time for a reason. And that was when we figured out that we wanted to relate number of electrons that a reaction produces. And then this would be for a mole of them. That's their charge. We wanted to relate that to delta reaction G. But this is charges, this is energy. Amount of charge per mole, that's joules per mole. I had to have a translation. It was E. Voltage, which we don't call V in chemistry, we call it E. I don't quite know why, it's a little stupid. Okay, now I'm missing something, it's a minus sign. That's Ben Franklin screwing up, thinking electrons were positive. Okay, now that gave me this relationship. Now I have to actually put in the actual reaction G. So it's RT, ln, Q. And Q is K, just not at equilibrium, so you just come up with it the same way. But engineers, you know what optimal batteries? They often have Q equals to 1, and so that's why I kind of tabled it. So what happened then was, we then figured out that we wanted to solve for E minus delta reaction G naught per mole, that doesn't do anything, divided by the number of electrons, divided by Faraday's constant. Again, that's just the amount of charge that a mole of electrons have. And this ended up being the standard EMF. Okay. And then we worked problems where maybe I'll send you some examples later on. But we worked a bunch of problems where you have two half potentials, figured out which side wins, which side is the driving energy, the driving G. Voltage is not energy. It obviously related to energy via the Nernst equation that's up there, but it is not energy. So energy always wins. So whenever you write down two half potentials, you have to just figure out which one has the most negative delta G, then conform the other one to that one, and then actually just add the voltages and you got it right. Last bit, and I'll spend 1 minute on this, was I had P versus T diagrams. This is after the first test. I can see myself just throwing this at you, seeing whether you really understand what the heck it is. I can already tell this is water, solid, liquid, gas, are critical. And okay, that's boring, that's high school stuff. We then were able to figure out why there's only one triple point, why I have lines, which was the Gibbs phase rule. Number of components, in this case 1. Phases, well, if I have one phase, then I have 2 degrees of freedom, meaning I can change temperature and pressure and still keep the liquid. Last thing we went over is how to calculate these lines, and that was to match chemical potentials of phase alpha. So we had to do this. Sorry, I know I'm going kind of quick. I'll find a clever way to make it up to you. And we had to match that to the kilometer. Just 1 second, folks. Because there's one last thing I wanted to bark at you. Because I had this, and then what I was able to do is do dP dt. And by the way, if I have one of these questions on the final, I'm going to have the equations written out for you. This will be an example of, I'll give you an equation and just see whether you can actually use your calculator. All right, this is the Clausius-Clapeyron equation. And from this, not with entropy, entropy is too hard, but since I live in a world of constant temperature and pressure, I know that actually the change in entropy is actually change in H over T times the change in volume per mole. Then, what you can do is I have to give you this, or if this is a gas, then the change in volume was approximated as the change in gas. And then you can bring dt over here, integrate them, and then knowing where your starting points are, you can then use that equation that Azra went over and build up all of these points, as long as you have some idea what you have to know what h is, and you have to know what the change in volume is, in the integration, and blah, 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 blah. Anyway, okay, so that's just kind of nice. It's nice that you have to have a starting point, but you can build a proposed diagram. Remember, it also explained why water slopes left, because this happens to be negative between the solid and the liquid, and everything else slopes right, because most liquids are less dense than solids. And then we went over a little bit about changes of volumes of liquids, about how, sorry, I'm ending right now, about how when you mix two liquids together, if I add water to water, I add a mole, it increases by volume by 18 milliliters. If I do it to a pure vat of ethanol, its volume actually increased 14 milliliters. Guess what? Not on the test, because I didn't really cover it there. So I'm done. And I got one last thing that maybe you ought to know. I already know some of you have been checking your email. The rest of you might want to do the same. You see, 5 minutes before class began, I sent you a little document. Actually, it's a rather large document. 5 minutes before class began, I sent you this. Check your emails. You didn't have to write any of this down. I gave it to you 2 hours ago. And I've got one more trick. Look, you need to write it down. It helps. I've got one more surprise for you, by the way. Wait for it. You'll see it. Sorry to be a dick. It's in your best interest, all right? And I will see you all on Wednesday. I don't feel good.